Okay, welcome back to my awesome math class. The book that we're using is available online for free. I put the address in the comments, and also use the Humongous book of algebra problems to help me think of ways to teach you this. In this case, what I'm going to do is I'm going to talk to you about chapter 0.4. We're still doing pre-algebra, and we're going to study the properties of algebra. So this is something, again, you should have learned in your other class. But anyways, I promised at the beginning of the show I would not say this is something you should have learned in your previous class. So we're going to go over it as if it were the first time you were doing it. Okie dokie. So, pre-algebra properties of algebra. Objective is to simplify algebraic expressions, which really means things containing x and y, by substituting, giving values, distributing, and combining like terms. So we're going to obviously build on what we've already learned in the other chapters. So it says here, in algebra, we often need to simplify an expression to make it easier to use. There are three basic forms of simplifying, which we will review here. And then there's a little world view note that says the term algebra comes from the Arabic word algebra. I don't know if I pronounced that right, which means reunion. It was first used in Iraq in 830 AD by Mohammed something. The first form of simplifying. So it's really interesting how a lot of many of the innovations from about, I don't know, 800 to 1200 AD come from the Arab world, because back then they were like, I don't know, they were like the center of the civilized world. So let's continue reading. The first form of simplifying expressions is used when we know what number each variable in the expression represents. If we know what they represent, we can replace each variable with the equivalent number and simplify what remains using order of operations. So what does all that mean? Well, they want us to replace letters with numbers and complete the equation. That's what it really means. So when they say replace P with 3 and Q with 5 in example 30, well, let's do it. Okie dokie. So it says here, just a moment, P, Q plus 6 when P equals 3 and Q equals 5. So what does P equal? We'll just write it underneath, 3, and Q equals 5. We'll put it underneath. So let's rewrite this equation, 3, 5 plus 6. So remember the order of operations. We do parentheses, exponents, multiplication and division, addition and subtraction. So here we're going to do 11. All right, 5 plus 6 is 11 times 3 equals 33. Well, that's your answer. So let's do this. Whenever a variable is replaced with something, we put a new number inside a set parentheses. Notice the 3 and 5 in the previous are in parentheses. This is to preserve operations that are sometimes lost in simple replacement. Sometimes parentheses won't make a difference, but it's a good habit to always use them to prevent problems later. I have no idea what they just said there. Just follow the orders of operations. So let's look at a more complex example. X plus zx, 3 minus z, x over 3. Where x equals minus 6 and z equals minus 2. So let's remember we do parentheses, exponents, multiplication and division, addition and subtraction. All right, so let's rewrite this. So that's minus 6 plus minus 2 multiplied by minus 6. You're seeing that, huh? The z here, the x is there, this is here. And anytime you have two variables, these two buggers here, two letters, stuck together like this with nothing in between. See the zx here? See the zx here? That means they want you to multiply it. And I didn't pull a multiplication sign to show you that this is what this means. It means multiplying. Here, there's nothing between the x and this bracket, so you're also multiplying. So let's put another bracket. 3 minus 2, right, multiplied by minus 6 over 3. Look at that one goes right there. You can always pause it and check if you want. Okie dokie. So now we've got numbers. Now we've got to do the orders of operations. So first thing we do is parentheses. Is there parentheses? Yes, there are around individual numbers. This one, this one, this one. This one is a number. It's actually to divide. But this is the real parentheses right here. So let's solve for this. 3 minus 2. Well, every time you have two minuses, right? When you're subtracting a negative, it becomes a positive. 3 plus 2 equals 5. Minus 6 divided by 3 equals negative 2, right? There's only one negative. You're dividing this expression by this expression, or this number by this number, I should rather say. If one of them is negative, it's a negative answer. So that's a minus 2. So let's carry down what we have. Minus 6 plus minus 2 times minus 6 times 5 times minus 2. Boom. So do we have any more parentheses here? Not really. Do we have any exponents here? Nothing. Do we have any multiplication or division? Yeah, we've got this, this, this. So let's start multiplying. Minus 2 times minus 6 equals 12, right? Two negatives make a positive. Multiplied by 5, that equals 60. Multiplied by negative 2, that equals negative 120, right? I'm multiplying a positive by a negative, that's negative 120. So I have, carrying this down, minus 6 plus minus 120. So since we're adding two negatives, it makes an even bigger negative. Minus 126. What's our answer? Yes, it is. That's a good answer. So that's the explanation of that. Let's continue reading. It will be more common in our study of algebra that we do not know the value of the variables. In this case, we will have to simplify what we can and leave the variables in our final solution. One way we can simplify the expression is to combine like terms. Like terms are terms where the variables match exactly, exponents included. Exponents included. Example of like terms would be 3xy and negative 7xy, or 3a squared b and 8a squared b, or 3 and 5. If we have like terms, we are allowed to add or subtract the numbers in front of the following variables. Then keep the variables the same. This is shown in the following example. 5x minus 2y minus x plus 7y. Combine like terms. Now this is where it becomes very complicated. Why in the world would we put letters there instead of numbers? If you look at the previous example, we were putting numbers in the letters and then it all made sense. We could add it and subtract it and multiply it and do whatever. Here we're blocked. Why in the world would we put letters instead of numbers? The answer is simple. We put letters there because we don't know what the numbers will be. And I think to myself, how come we don't know? Well, there may be all kinds of situations that we don't know. I'm going to show you a spreadsheet. Suppose one day you become rich and you begin selling iPads. You don't know how many you're going to sell in a given month, right? So if you're going to find out how much money you're going to make, depending on how many iPads you sell, you're going to need to set up not like letters which can be filled with any number to obtain the results you want. So for example, let's say you sell one iPad. So the sale price of an iPad, let's say, is $800. And you sold one iPad. And it cost you $500 to make an iPad. Well, in the case there's only one, right? So here, $800, you sold one iPad for $800. So therefore you have, let's do it, You have $800 because you sold an iPad. And it costs you $500 to make every single iPad. Let's go back here, 500. So your profit is 800 minus 500, right? I paid $500 to make the iPad. I sold it for $800. I got $300 left over. But what if I sold more iPads? Well, then this number would change. But I don't want to change the equation every time because the number of iPads I sell can be different. The sales price can be different. I might want to bring down the price a little bit or bring it up. And the cost might become less or more over time. You don't know what happens. Your employees might charge more money to make the iPads. The materials, the glass that you use to make the iPads might go up in price or go down in price. They're going to change. Well, you're not going to be thinking 800, 100, 500. You're going to be thinking in X, Y, Z, where X is going to represent the sales price of the iPad, Y is going to represent the number of iPads sold, and Z is going to represent the cost of making a iPad. And those numbers can change, but you want an equation that will be able to work no matter what these numbers are. That's a pretty good example, I think. Moving along. So we're combining like terms. We'll get to that in a second. So what they want us to do basically is to combine like terms. So let's take a look at this. 5x minus 2y minus 8x plus 7y. Now, what they're saying here is that in this equation, this will always be a 5 in this equation. This will always be a 2. This will always be an 8. This will always be a 7. This will always be an x. This will always be an x. So if you decide to say x equals 25, no matter what, that x, these two x values will be the same. Now at this point, I want to say x can be worth anything. But what I'm saying is these x's will always be the same. So we can combine them. Now let's look at this more in depth. Let's say x equals 25. So let's take a look at this and take a look at this. So it's going to be 5x minus 8x. That will equal something. If I put x at 25, 5 times 25 minus 8 times 25 equals 5 times 25 is 125 minus 200 equals minus 75. But we can't do it like this because they're not giving us what x means. They want us to combine like terms because we don't have that information. So we'll do, in this case, we'll do 5x minus 8x equals, they want us to combine these two. So it's going to be 5, it's like saying 5 minus 8 equals negative 3. And don't forget to add the x. Because you're not just doing 5 minus 8, you're doing 5x minus 8x equals minus 3. So if we had x equals 25 like the previous equation, we would do minus 3 times 25 equals, and that would be 75. Now the difference between this equation and this equation, there is no difference. Here you assign a value to x. Here you can put any number and solve the equation.